Morning, guys. So today I'm going to take a topic which is unrelated with the topic which has been discussed during the live class. I have done an approximation. This much topic I will be covering during the live class. Based on that, I am continuing. Okay. So today we'll be starting. Actually, I believe to start with Bernoulli's theorem, but before that, some terms I want to clarify. After that, we'll go for Bernoulli's theorem. Okay. The topic is the energies, that is in the case of streamline flow you have to learn some terms which is required in Bernoulli's theorem also. Okay, so first term is what is the kinetic energy per unit volume of a streamline flow. Kinetic energy per unit volume, right? So actually what is the actual equation of kinetic energy? It is half mv square. That is, I can write it as half into mass can be written as volume into density, and this is velocity. Okay, this v is velocity squared divided. Now okay, this is our kinetic energy equation. Let's make this as like this, because 2v looks like same. So this is velocity square, right? So that the confusion doesn't come up, right? Let me make this as v squared. This is velocity squared, this is volume, right? Now kinetic energy per unit volume then becomes what? Divided by v, then it becomes half rho v square. This is kinetic energy per unit volume of a streamline flow. Okay, right? Now similarly, someone asks you what is potential energy per unit volume, right? If a liquid is flowing by a distance h, right, from a distance height h, it will be having a potential energy. Then potential energy, it is mgh, that is, I can write it as rho into volume, that is mass, into g into h divided by volume. Why? Potential energy per unit volume. So this volume cancels out, so I can write it as rho gh, right? So this is actually, we can say, is the expression for potential energy per unit volume of a streamline flow. Now very similarly, there is a new term which you have to know, that is pressure energy, right? I will talk about pressure energy first, then I will say what is pressure energy per unit volume. So what is pressure energy? The energy or the work done by a pressure on a liquid, right? Suppose there is a pressure P is acting on a liquid which is passing through a cross-sectional area of A, right, and passing through a distance x, then work done, you will write it as work is equal to force into distance, that is for distance or displacement, you will write it as F into x. F can be written as pressure into area into displacement. Now area into displacement is volume, that is P into V. So this is pressure energy, that is P into V. So what is pressure energy per unit volume? You will divide it with V, V cancels, so P. So pressure energy per unit volume is pressure P. That is how much pressure acts on a unit volume of liquid, that is P itself. Easy, right? So you just have to know the terms, something which you know, but you have to know the terms. Clear? Now similarly, let's move on with the, I told you I will talk about Bernoulli's theorem, right? So let's move on with Bernoulli's theorem. Bernoulli, Bernoulli's theorem. Right? Now what does the Bernoulli's theorem state? That is, in an incompressible and non-viscous liquid, if an incompressible and non-viscous fluid flows in a streamline motion, its total energy per unit volume remains constant at every point of that streamline flow. See, when I say the statement, I prefer you guys write it down on the notebook itself, because it is difficult to write on the board. So I am repeating Bernoulli's theorem. If an incompressible or non-viscous fluid flows in a streamline flow, it is very important. This should be streamline flow, not a turbulent flow, right? It is moving in a streamline motion. Its total energy per unit volume remains constant at every point of the streamline. This is what is Bernoulli's theorem state. I will explain it. Right. See, that is, suppose if I can say in layman language, Bernoulli's principle states that in a streamline flow, sum of pressure kinetic energy per unit volume, that is half rho v square, and potential energy per unit volume, that is rho gh, right? Sum, right? So I'm going to remove this commas, that is plus plus, they are all constant. This is what is stated by Bernoulli's theorem. This is a mathematical expression of Bernoulli's theorem. Sum of total energy. This is the total energy. Pressure. This is kinetic energy per unit volume. This is potential energy per unit volume. It is always constant at every point. Clear? Right? That's why I introduced these terms before. Clear? Now we are going to derive the Bernoulli's theorem. So there's few assumptions you have to make before you go for the derivation part. Assumptions are, first assumption is the fluid is flowing through a pipe of varying width. I will draw the figure. Just you will take a figure of pipe like this, right? So varying width. This is having higher width. This is lesser width, right? So we'll consider a pipe which is of varying width. The next is, there is a, the next one is the pipe is located at different heights, right? This section was lower, this section was higher, right? And fluid is incompressible in nature, that is the volume doesn't change depending upon pressure. The flow is laminar or streamline, and no energy, there is no friction here, right? So smooth formation or smooth flow, hence there is no friction. These are the following assumptions we are going to take. Right, now we are going for mathematical derivation part. Clear? So let us consider the figure for Bernoulli's theorem. I have already drawn it because it takes time to draw, obviously. So look into the pipe, right? It is of different area cross section of, and each end is at different height, and we are going to assume a streamlined flow is going to happen here. This much clear? And incompressible fluid is going on and no friction is there. Okay, suppose consider the fluid is initially between B and D, this position, right? Initially this end and this end, right? And let's say during a time interval delta t, the fluid has moved from B to C, and similarly from this end D to E. That is, from position BD, the liquid has shifted to CE, right? Clear? Suppose V1 is the speed at B, as I have not written here. Let's say V1 is the speed at point B, right? And V2 is the speed at D. So during the time interval delta t, this much distance has been covered here. So that I am going to write it as V1 into delta t. Right, and during delta t interval, the position of liquid has changed from D to E, so that distance I have written here as V2 delta t. Right, clear? Now pressure at this end is P1 and pressure at this end is P2. Clear? Now at the left end, right, from B to C, a work has been done, right? Let's write that work, work done at this end, on the fluid end, or work done on the fluid at the left end BC, right? W1 is force into distance, right? Now force, I can write it as pressure into area, so I am writing it P1 into A1, right? And distance is V1 into delta T, right? That much distance, so I am writing it as V1 into delta T. Right, now here work is done on the fluid. Here the work will done by the liquid. Why? Because of high potential energy, so it can come out, right? The liquid can come out by itself, so there the work is done by the fluid on this end DE, right? So I'm writing it as W2, right? It is equal to P2 into A2 into V2 into delta T, right? Now what will be the net work? Net work is the difference between the work here, right? Because one is work done on the liquid, and this is work done by the liquid, right? This is on the liquid, this is by the liquid. So net work done is W1 minus W2, that is equal to P1 A1 V1 delta T minus P2. I could have changed here, so here write P2 A2 V2 delta T, right? Clear? Now we know by equation of continuity, I hope you remember this AV is constant, right? Right. So I'm writing here AV is constant by equation of continuity. While you write, you should maintain, let me make this one as 1 point, this is 1 point, right? Right, so this is another point. So I recommend, while I have written here AV is equals to constant, you in bracket write it as equation of continuity, right? Now, so AV is constant, right? From here in this equation, right? Here A1 V1 delta T, right? And is actually equal to what? This is area into distance, right? So it is change in volume, right? See, this is change in distance, this is area into volume is what? It is volume, right? So actually I can write W1 minus W2 is equal to P1 change in volume, right, minus P2 into change in volume, right? Clear? Or I can write here delta V is into P1 minus P2, right? You get a equation for W1 minus W2. Now we know, right, part of this work which you have calculated now is changing the kinetic energy, right? So change in kinetic energy, how would write? I would write it as half m v2 square minus v1 square, that is a change in kinetic energy, and part of the energy is changing in the terms of change in potential energy, that is mg h2 minus h1, right? Clear? So the total energy change will be sum of these two one, that is I would write it as total energy change. Total energy change is equal to sum of these two guys, that is half m v2 square minus v1 squared plus mg h2 minus h1, right? Right? Clear? Keep this equation here. This is required. Let's make this equation as equation say 1. Right? Let's make this as equation 2. Clear? Right? This much we have written. Right? Now what is density of the fluid? Rho, that is equal to mass by volume. Right? Or I can write mass is equal to density to volume, which we have learned, right? So during a time interval of delta T, right, there will be a small mass change, that is delta m, that can be written as rho. Density is not going to change, volume is changing, that is delta m is equal to m into rho v, right? Now this expression I'm going to put in the total energy change, right? Clear? So here actually mass, actually I was supposed to write it as delta m because the mass is changing, so in place of m, right, or if you want to write here m, I will write it as rho into delta v. The mass is very small, guys, only a few amount of fluid shift I am going to consider, right? So actually I was supposed to write it as delta m, but for you guys, when I suddenly start to write delta m, it looks odd, right? So here in this expression I am going to write for total energy change is equal to half into rho into delta v into v2 square minus v1 square plus, right, mgh, I'm going to write it as rho into delta v h2 minus h1, right? Happy? Clear? I missed a g, so there is a g. Clear? Now total energy change, you have learned work energy theorem, right? In work energy theorem you have learned work is equal to total energy change, right, or energy change. So in place here total energy change, I can write works equation, we have found it as P1 minus P2 into delta V, right? So half rho delta V V2 square minus V1 square plus rho delta V H2 minus H1 into G. Now this term has delta V, this term has delta V, this term has delta V. So I removed all of this and I can write it as P1 minus P2 is equal to half rho V2 squared minus V1 squared. What would I do? See, this isn't our velocity now, so you will confuse later on, right? So I recommend here the velocity section, etc., make it as this symbol. If not, if you are not confused, then it is okay. Plus rho H2 minus H1 into G, right? So you got an equation. Now what I am going to do is I am going to rearrange this entire equation, so that one terms I am going to bring in the left hand side, P1. Then there is a one term here. So plus half rho V1 square. V1 square. Then I am going to bring this H1 term here, plus rho H1G is equal to, P2 goes over here, P2 plus half rho V2 square, right, plus rho H2G, right? So you see this term, this looks like this one is P1, this is P2, half rho V1 squared, half rho V2 squared, rho GH1G, rho GH2G. Or I can write, see, P plus rho V squared plus rho GH is constant. This is sum of energies at this end. Remember, in this figure, sum of energies at this end is equal to sum of energy at this end. That is what this meant. This equation meant, and which we can write in this form as pressure energy per unit area plus kinetic energy per unit area. So not unit area, plus unit volume, sorry. Pressure energy per unit volume plus kinetic energy per unit volume plus potential energy per unit volume at every point of a streamline flow through a pipe is equal to constant. Clear, right? Clear? This is the derivation part. Most of the time this derivation is as it is asked for examination point of view. Now we are going to deal with special cases of Bernoulli's theorem. Right? See, that is, let's say the fluid is at rest. So velocity V1, V2 all will be at 0. That is a special case. First I am going to say the fluid is at rest. So your equation P1 plus half rho V1 squared plus rho GH1 will be equal to half rho V2 squared plus rho GH2, right? Clear? Sorry, I forgot a pressure term, right? P2 here, right? So this is our general equation we have derived for Bernoulli's theorem. What happens if I put V1 and V2 0? So this term goes off, that is kinetic energy per unit volume goes off, right? So P1, and let's bring P2 in this side, P1 minus P2 will be equal to rho G H2 minus H1, right? Why did I write a square here, right? Right, so this is same as that of the liquid. See, this derivation I have done before itself, right? This is the equation same as that the fluid at rest. Remember, we have derived this equation, right? Now similarly, second case, let's say if this is the first case, so the second case, let's say the height is same, that is the pipe is horizontal in this way. So height H1 will be equal to H2, right? So then no potential energy change will be there, right? This term goes off, this term goes off, because this will be rho GH1 and this will also be rho GH1. This term and this term goes off. So I can write it as P1 minus P2 will be equal to half rho V2 squared minus V1 squared, right? Right, or we can just simplify it, right? Pressure plus half rho V squared will be equal to constant. Your potential energy per unit volume term goes off. So there are two special cases, right? There is no, in this case, when both the height are same, that is the pipe is horizontal, there is no potential energy by virtue of height. when this condition is considered, when the pipe is such a way that there is no flow, that is the liquid is stagnant as it is, then you get a general equation of pressure change at 2 points. Clear? Simple. Right. Now we will go with the application of Bernoulli's theorem. So this and all are actually straight away asked. Okay. So there is an alternative, before going for application, there is an alternative statement. Alternative statement of Bernoulli's theorem. Right, it is conservation of energy, right? Actually, Bernoulli's theorem is a statement of conservation of energy by the flowing liquid. If maybe rephrased, right, we can rephrase the entire thing. We had the equation, I'm going to write it as again, P plus half rho V squared plus rho GH is constant. This is our Bernoulli's theorem, right? What I'm going to do is, I'm going to divide the entire terms with rho g, right? So this becomes P by rho g plus half rho v squared by rho g plus rho gh by rho g, that is constant. Constant by rho g is constant itself, right? Now quadrant I can remove. From here I can remove rho g can be removed, or I can just rearrange it so that it becomes this term, P divided by rho g, and this term becomes half V squared by 2g. Okay, let's remove this half, V squared by 2g plus h is constant. So this is another way of writing, right? Now you see three terms here, this V squared by 2g, P by rho g and h. This and all are given special names, right? Clear? So V squared by 2g is called velocity head. Velocity head, right? And this term is called pressure head, right? And the H is called gravitational head. Gravitational head, right? Clear? So this is another form of writing Bernoulli's theorem. Obviously the first section which I have taken, that is the actual way of writing Bernoulli's theorem, but this can be also represented as or called as Bernoulli's theorem statement itself. Clear? So this is pressure head, velocity head, gravitational head, right? That is, velocity at any point of the flow is related to a effective height or head. Height is the meaning, or height is the term which you go for head. Clear? Right. So this is an alternative way of writing Bernoulli's theorem. After this we will go for application of Bernoulli's theorem, and first application of Bernoulli's theorem is basis for another law. Application of Bernoulli's theorem is Torricelli's law. Not the first, next, this is the first application you have learned, sorry. Torricelli's theorem or Torricelli's law, right? Or it is called velocity of efflux of a fluid. Here we will be talking efflux. I will tell you what is efflux. That is, suppose the flow of liquid through a narrow orifice. Orifice means a hole. Suppose there is a large vessel, you make a hole, drill here, this becomes an orifice, right? So we will be dealing with the velocity by which a liquid flows out of an orifice, right? So that has been, or that can be found by Torricelli's law. First I will just recite the theorem. Torricelli's law states that the speed of flow of a fluid from an orifice is equal to the speed that it would attain if falling freely for a distance equal to the height of the free surface of the liquid above the orifice. I hope you didn't understand anything. So I read the theorem, right? Pause the video, write the theorem complete as it is. Now I'll explain what the Torricelli's theorem states as per a layman language. Suppose there is a tank like this and I drill a orifice. Orifice means a hole, and the liquid is coming out, right? Let's say the orifice is at a height h from the surface of the tank, right? So the velocity by which the liquid flows out, let's say, is v, right? So I hope this is understood, right? Now if I consider it an object, right, at this position which is at a height h. For this object, I'm not going to consider this part as ground. We're going to consider this h as its height, right? So this object will be also moving with the velocity v. This is what Torricel's law state. That is, if I consider an orifice, right, from there the liquid will moving out with the velocity same as that of the velocity an object freely falling body will be attaining at a height h from the position of orifice to the surface, right? That is, if I consider an object, right, that object which is freely falling body, that object, let's say, is at a height h from the orifice, right? Clear? Right? That will be having the same velocity as that of the liquid which is coming out of the of the orifice, right? And this orifice is at a distance h from the surface, right? Clear? Right? This is what is said by the Torricel's law, right? So I recommend you to read the law and then understand it. Clear? I hope you understood, right? Now we have to derive the entire thing, right? So again, for deriving, we have to draw a figure, right? So let us consider this as a tank, right? Let's consider there is an orifice here. Water is going to, or liquid is going to form out here, right? Let's say the liquid is falling like this, right? Let's say this position is y1 from the downside, and this top surface is at a distance y2 from the ground, right? Let's say this height I have marked it as h, right? Clear? Right. Now let's say this area, the small area, is a1, and the liquid coming out with the velocity v1. Let's say here, as the liquid goes out, right, here the area is larger. I'm going to take it as area a1, and the liquid will be coming down, right? So let's say the liquid is moving down with the velocity a2. Let's make this as a2, right? This is a1 now. a1 v1, a2 v2. This much is clear, right? That is, a1 is the slit area, v1 is the velocity with which the fluid is coming out, a2 is the area of the free surface of the fluid, right? And v2 is the velocity of the fluid at the free surface. This much clear, right? Now we learned about equation of continuity earlier. What does it state? Is a1 a1 v1 is equal to a2 v2. We have learned it, right? Now figure itself is showing that a2 area, this area is very, very large when compared to this area, right? Clear? So this means that if a2 is greater than a1, then obviously v2 should be very, very less than v1. Then only the equation of continuity can be true, right? When area increases, velocity has to decrease, right? So this much is clear. So v2 is less than v1. This means the fluid is comparatively at rest at this point when compared to this velocity, right? The flow of liquid in this direction downward is less when compared to the liquid flowing out of the orifice, right? Now that's why we are going to assume that velocity v2 is equal to 0, equivalent to 0, right? Not equal, equivalent to 0. Clear? Now Bernoulli's theorem we have written as P plus half rho v squared plus rho gh is constant. This is Bernoulli's theorem, right? Now we are going to apply this Bernoulli's theorem at this slit portion. So let's say this is atmosphere, right? So the pressure at this point will be atmospheric pressure Pa plus half rho v1 square, that is the velocity at this end, plus rho g, this orifice at its height y1, so I will write it as rho g y1, right? This becomes okay, let's write it as equal to constant. This is equation 1, right? And now guys, clear? This much is clear, right? Now what I am going to do is we are going to apply Bernoulli's theorem at the surface also, that is here. So where can I write? Let's make this a small, right? So I will write pressure. Now I'm going to apply it on the surface. So pressure, right? Plus here the velocity we have assumed to be 0, right? So what I am going to write, this term kinetic energy per unit volume term goes off at this end. So it will be pressure plus rho g y2, because that is the height of this free surface, that is equal to constant. That is the second equation. So you got two equations, right? Clear? Right. So equation and equation 2, what does it mean? It is application of Bernoulli's theorem, and we have said that the sum of kinetic energy is constant throughout. So these two equations should be equal, right? So I will write PA plus half rho V1 squared plus rho GY1 is equal to P plus rho G, no, why did I write it as G2? Rho GY2. I equated these two guys. Now what I'm going to do is I'm going to bring pressure terms at one side. So it becomes half rho V1 squared is equal to P minus PA plus rho G. I'm going to Y1 and Y2 one side. So it becomes Y2 minus Y1. Y2 minus Y1. Right? Right, you got an equation now like this, right? Now what is y2 minus y1, guys? Look at the figure. From y2, if I remove y1, what I get is h, right? So can't I write in place of y2 minus y1 as g rho g h? Yes, right? So half rho v1 squared is equal to p minus pa plus rho g h. Right? Clear? Now let us just find velocity v1 squared. So that becomes rho v1 squared is equal to 2 into p minus pa plus rho gh. Yes? Now let us divide rho in this denominator. So this rho goes in the denominator, so it becomes 2 by rho. Right, let us just find v1, that is velocity of the liquid which is coming out, so it becomes root. Right, now you got the velocity of the liquid which is coming out of the orifice, and this velocity is called efflux. Right, this velocity is called efflux, right, or speed of efflux. Right, that is the speed of the fluid outflow. Right, this equation you have derived now we have derived the equation of efflux. This is not the final equation, guys. Not the final means we have still not reached the Torricelli's law as it is. Right, the speed of efflux v1 from the side of the container is given out. Right, so we have used Bernoulli's theorem as well as equation of continuity to find the value of speed of efflux through an orifice. Right, now write the special cases. Now let us talk about case 1. Right, suppose the vessel is not closed, it is open. Right, open in the sense, see, we here drew a closed container. What I'm going to do is, let's say this section is open. Right, sorry. So when that is open, I can say the pressure at that end, which we assumed as P. Yes, remember here we assumed the pressure is P. That pressure I'm going to change into atmospheric pressure. Right, that will change into atmospheric pressure. So there I can say P became PA when the container was open. Right, when P is equal to PA, let us talk about this equation. Then P minus PA, right, P is PA, PA minus PA is 0. Right, so this term goes off, so I can write it as V1 is equal to root of, right, 2 by rho into rho gh. Right, now rho cancels out and you can write root of, now you got an equation, root of 2gh. We have learned this equation before. Right, this is the velocity of a freely falling body from a height h. Right, this is what we just talked about Torricelli's law. Remember? No, let us take, I will draw it again. We drew a figure like this. Right, and there was an orifice, right, and the orifice is at a height h. So the velocity by which the liquid comes out, that is v1, which we have written, right. Now this at the same height, right, if I had kept an object like this, right, at this height h, so the object will be moving out with a velocity v. What velocity? It will be root 2 gh, this height, right, and we just found this velocity velocity is root 2 gh, and this velocity is also root 2 gh if this container is open, right. Clear? Right, this is Torres's law which we just stated. So we found that an object, if it is kept at a position h from the liquid free surface, right, so this is a free surface. Let's say the free surface is like this, right, and the object is kept at a height h from here. So it will be moving out with a velocity, freely falling body will be having velocity v is equal to root 2 gh, right, at the same height, right, if this container is open at the same height there is a orifice, so the liquid coming from this orifice will be also having velocity root 2 gh itself. Clear? Right. Now this case 2, let's say the tank is not open, so the upper pressure will be very high when compared to the atmospheric pressure, right. So you can actually disregard 2gh value, right, because it will be very large, right. See, when pressure is very high, right, so this term sections 2gh terms, right, 2gh, this term when I multiply inside this one, what happens, this will be equal to root of 2p minus pa, this is p, okay, divided by rho plus rho cancels out, becomes 2gh now. So you can remove this term because this term will be very high, so your value of equation will be just equal to what, v1 is equal to root of 2p minus pa divided by rho. Now we just said that the pressure p will be very high when compared to atmospheric pressure, so I can remove this atmospheric pressure, right. So the v1 will be equal to root of 2p by rho when the container is such that the upper surface is fully closed, right. So here at the case 2 condition I can say v1 will be equal to root 2p by rho. Clear? Right, the velocity with which the fluid will come out of the container is determined by the pressure at the free surface of the liquid when the container is fully closed. When the container is open, the effluent will be having the same velocity of as that of a free falling body. Clear? Right, so shall we move on to the next section, which is Venturi meter. Venturi meter, that is the next application of Bernoulli's theorem. Venturi meter. So Venturi meter actually is a device, right? It's a device to measure the velocity of flow of a liquid in a pipe based on Bernoulli's principle. So it is used for measuring the velocity of flow of a liquid. So the device is actually a tube with a broader diameter and having a larger cross-sectional area. But there is a small constriction in the middle. That is, if you draw the Venturi meter, it looks like this, right, broader at this end and there is a constriction at this middle. So this is how a Venturi meter looks like, right. And this Venturi meter is first, if suppose you want to measure the velocity of a liquid which is flowing through a tube, then usually it is having there will be three openings here, right. So these three openings, you can select either these two or these two, like this. One end should be obviously from the restriction and the other two or end can be either this one or this one, right. So let us only consider one set, that is one from this broader end and this from this end. I will remove this, right. So this is how a Venturi meter looks like. Let us consider to connect this Venturi meter with the U-tube manometer. So let's connect it with the U-tube manometer like this, right. Okay, right. And let's say this U-tube is filled with the fluid of density, let's say rho, Oh, the blue doesn't look good here. Okay. Okay. This looks odd, it's okay, right? So we have filled it with the liquid. This much clear? Liquid which is having density rho, right? Let's write here density rho. Oh, this became very small. Okay, right? Now A1 is a cross sectional area at the broader end. This one is having area A1 and velocity of the fluid here is V1. So the venturimeter is having, or the liquid which you want to measure its velocity, that liquid is, let's say, moving here. So there is a constriction here, right? So there will be different areas. So let's say this constriction is having area E2 and the velocity here, let's say, is V2. Let's make this V in this way, right? This much is clear. Now we know by equation of continuity, area, how much area more, that much less will be the velocity, right? So since the area A1 here is more, here the velocity will be less, and here the area is less, the velocity will be more. That much common sense you have, right? So I hope you understood the area velocity relationship. But the problem here is, here we have just told you we have the areas higher, velocity low, areas lower, high velocity high. See, but there is a very important concept while you are talking here. We have not considered pressure here, right? So pressure is a very important section, because in Bernoulli's theorem we have written P plus half rho V squared plus rho GH is constant, right? Now here there is no height difference, so you can neglect this term. So rho GH I can remove. So I can say P plus half rho V squared should be constant, right? Now if I have to keep, suppose the pressure increases, right? If the pressure increases, in order to make this pressure constant, rho cannot be compromised, half cannot be compromised, so velocity has to reduce. A very important concept. This is not explicitly mentioned in your textbook, that's why I am taking here. So we just found that, see, area is higher, so here area is higher. Which one part? The area is higher, right? So here area is higher means we know pressure is inversely proportional to area, force by area, right? So when area becomes higher, obviously the pressure will be what? Low, right? So I can significantly say that here area higher, so P1 is less than P2, right? Here the pressure will be less. Now in order to maintain, so the pressure, if it is higher here, sorry, lower in this condition, means velocity here has to be increased. Then only this term, that is Bernoulli's theorem, will be constant, right? So if P1 is less than P2, that means V1 should be greater than V2. Keep this in mind. This is based on the Bernoulli's theorem. Keep this in mind. So when pressure increases, the velocity decreases. When pressure decreases, the velocity increases. So when P1 is greater than P2, V1 is greater than, sorry, P1 is less than P2, then V1 is greater than V2. Keep that in mind. This is not explicitly mentioned in your textbook, but they have just mugged up a lot of steps. Then the area is greater than blah 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 blah. So it is very difficult to understand by just reading the textbook. That why I took it. Why? Because most of the time kids say like this. See, area increases, velocity has to decrease. So why here area is higher? Still in the textbook it is given velocity is lesser here. Why? That's why I'm taken here. Again I'm repeating. See, A1 is greater than A2, right? If A1 is greater than A2, so that means P1 is less than P2, right? So if P1 is less than P2, that means P1, the pressure has decreased. In order to maintain the pressure, velocity has to increase. So V1 is greater than V2. Clear? Based on Bernoulli's principle. Clear? So I'm repeating here, right? So make sure you understand it. Now moving on. So as there is difference in the pressure in the fluid, right, moves, this movement in the fluid is marked by the level of fluid increase as per the end of the YouTube manometer, or this YouTube, right? Clear? Right. So I hope this much is clear here. So let's say here I have written the pressure, I have not written. No? Let's say the pressure here is P1, here the pressure is P2. Clear? Right. Now we are going to determine the fluid speed. So we have written A1 V1 is equal to A2 V2 by our continuity principle. So from here I can write V2 is equal to A1 by A2 into V1. Right. Let's make this as equation 1. Now we have written in Bernoulli's theorem what P1 plus half rho V1 squared plus rho GH is equal to P2 plus half rho V2 squared plus rho GH2. Now see, you can neglect these two guys. Why? Same height, no? Right? So I can here write it as P1 minus P2 is equal to half rho V2 squared minus V1 squared. Right? Now similarly, here what I'm going to do is I'm going to substitute this V2 value here. So this becomes P1 minus P2 is equal to half rho A1 by A2. The square is there. A1 square minus, sorry, by A2 square, and then V1 square minus V1 square. Right? We can bring V1 square common outside. Right? So it becomes P1 minus P2 is equal to half rho V1 squared into A1 squared by A2 squared minus 1. Right? Clear? So this is the pressure difference of the level of fluid in the U-tube manometer. Right? Let us see. If this end is having P2 pressure, this end is having P1 pressure, P2 minus P1 is the term which you have found here. Now, we have learned pressure difference between these two legs of the manometer. If there is a height difference H between these two height, that is, if I draw, this is the height difference. This is the level here. This is the level here. So, this is the height difference. Let's say that is H. Right? Clear? And let's say the fluid inside this is having, say, is mercury. Let's say this density is rho m. Right? So here P1 minus P2, I can replace it with rho GH. Right? So it is a rho m, density m, Hg. That is equal to half rho V1 square. Rho is the velocity of the fluid which is flowing through venturimeter. Right? So V1 squared into A1 squared by A2 squared minus 1. Alright? Clear? Right? From here you can derive the value of V1 squared. How? Let us bring the terms here. I'm going to bring 2 here. Then I'm going to bring rho here. So it has become rho Hg. That is equal to V1 squared A1 squared by A2 squared minus 1. Let us bring this term also this side. So it becomes 2 rho m by rho Hg whole divided by A1 squared by A2 squared minus 1, and there will be a root, that is V1. Clear? This is the expression for what? Velocity of the fluid which is flowing through this venturimeter. Right? Clear? Right? At this point, of course. Right? Clear? And if you want, you can even replace this V1 here and you can find V2 also. So you can find velocity at these 2 points. Right? Now, what is the practical application of venturimeter? See, spray gun or perfume bottle. Right? It is based on venturimeter. Consider bottle. Right? And consider that your bottle is filled with the fluid and having a pipe which has straight steel construction. I hope you remember the spray bottle, or you use some to spray water on the plants, that tube also. So there is a narrow end of the pipe which has a great cross-sectional area, right? The cross-sectional area, the construction which is at the middle is very less, right? You have this, I don't want to draw that figure, looks large, the pipe like this, and you will you have a bottle like this. right? So you will press here, right? So this constriction is less and this constriction is having higher area, right? And you will spray the water like this, right? Right, there is pressure difference. When we spray, as a result, some air goes in, the velocity of air changes depending on this cross-section area. Right, here the pressure change will be there. Here the velocity, suppose the pressure is high here, the velocity will be less here, like that. Right, so when you apply pressure here, right, you are giving pressure or air to this side, right? Yeah, so there is a cross-sectional area difference. The pressure is exerted over this end, but it is traveling at this end. So increase in pressure here means velocity decreases here, right? But here in this end, the pressure is less now. So that means the water can move higher velocity at this end. This is how it works. Clear? I hope this much is clear. Right, now let us move on with the next topic, which is dynamic lift. Dynamic lift, this is also an application of Bernoulli's theorem itself. See, suppose that is due to the dynamic lift. If you want, I can, okay, color changer, okay. Dynamic lift is the normal force that acts on a body by virtue of motion of a fluid. That is, suppose you consider the aeroplane etc. is working in the space. We can draw with an aeroplane itself, right? I hope you will feel this is an aeroplane. Why does it look like a fish? Right, okay. Suppose this object or this aeroplane is moving, right? And air you can just consider as a fluid, right? So, and due to the motion of this object or this aeroplane through the fluid, there is a normal force which acts on this body, and this force is acting here, right, because of which it is lifted. See, what happens is when the body is moving in the streamline flow, right, clear, in the aeroplanes, see, this aeroplane is moving in this air, so there is atmospheric pressure, right? When it is moving in this way, it is cutting the air, right? So the pressure above, or it is moving with a high velocity, right? When it is moving with a high velocity, the velocity or the velocity of air in this side and this side will be different, right? Velocity at the lower position will become less, and velocity at the above position becomes high, because it is cutting, so the air will be flowing more in this direction when compared to the lower position, right? So when the velocity at the lower position becomes less, that means the pressure will be higher here, right? Here the velocity is high means the pressure will be less at this point, so that's why high pressure here, so the aeroplane will be pushed up, right? And this pushed up movement is known as dynamic lift. Clear? Right? So next, similarly, another application of Bernoulli's theorem is this is something you can even see in, I would recommend, there is a video in YouTube, if you can write or just write application of Magnus effect. So this is the next section which I want to talk about, this Magnus effect, but you can see it in video. Just type a Magnus effect in YouTube, you can see a very beautiful video of a person doing an experiment about it. Right, now this is actually a type of dynamic lift system. Now dynamic drift by virtue of spinning, that is called Magnus effect. Right, this is something you see in football game etc. you would have seen, right? See, suppose a ball is spinning, right? So, and the ball is not spinning. We can consider two cases. Let's say case 1, the ball is not spinning. Case 2, the ball is spinning, right? So ball is not spinning, so move in air, it does not spin, just ball is move laterally like this, right? The velocity of ball above and the below will be same, right? So there is no pressure difference, so there is no dynamic lift. But when the ball is spinning and all, right, so when the ball is spinning like this, right, so it will be dragging air above it, right? So the velocity will be higher in this case and velocity will be lower in this end. So pressure will be higher in this case, pressure will be lower in this end. So when you spin the ball at a higher speed in this way, then with virtue of that spinning, the ball will be lifted above. And this is known as what? Magnus effect. right? A person is doing the experiment in YouTube video, you can see with the he's spinning the ball from a dam. That is this is a dam. He is spinning the ball from the upper position and is throwing downwards. So he sees that the ball is flying, not falling in this way, but it is flying like this. This is an example of Magnus effect. You can see it in YouTube videos. I would recommend it. Clear? Right? So let's move on with some numerical problems. Listen to this first numerical problem, guys. So you are having a copper, right, with cavity, right, and this copper with cavity is weighing 264 gram in air, right, whereas it weighs 221 gram in water, and the copper is having a density, say 8.8 gram per centimeter cube, and you are asked what is the volume of the cavity. This is the question, right? So as you can see in the question, I'm going to do the solution. Okay, so the copper has 264 gram in air, it weighs 221 gram only in water, means there has been a loss in weight, right? Now loss in weight will be 43 gram, that is the difference of these two guys, 264 minus 221 gram, and this loss in weight is actually the weight of the water displaced by this copper, right? Because the water which has been displaced is what had been given the buoyancy, and due to that buoyancy only the 43 gram is not weighed, right? So weight of the water displaced is 43 gram. Now if you are asked what is the volume of cavity, how can you find? You have to find the volume of the copper entire with cavity minus volume of copper only. You don't understand, right? Say, yeah, I will write like this: volume of copper plus cavity minus volume of copper. Then you can find volume of cavity, right? So what will be volume of copper plus cavity? Volume of copper plus cavity, that is a volume of water displaced, right? See guys, if this coin, this is the basin, I have kept the coin with cavity here, right? How much volume of water this entire copper has displaced, that will be equal to the volume of the entire thing, right? The object displaces its own amount of volume, right? So you have found that the water has been displaced is how much? 43 gram. So what is the volume of water displaced? Volume is equal to mass into density. So 43 into 1, density is 1, right? So the volume of water displaced is 43 what? Centimeter cube, right? So this much volume of water is displaced, means this much is the volume of copper and that cavity. So that is 43 centimeter cube. Minus what is the volume of only copper? Only copper means that is a mass of the copper by density of the copper. Now what is the mass of the copper? That is mass of the copper in air, that is 264 divided by 8.8, right? So 8.8, so you will get around 30. So 30 centimeter cube. So what is the volume of the cavity? It will be 13 centimeter cube. Simple. So you have to understand the concept. So it is very important to understand the concept, guys, right? Similarly, let us do another question. A cube wood is supporting a 200 gram of mass, right? A cube of wood supporting a 200 gram of mass floats in water, right? When the mass is removed, the cube rises by 2 centimeter, right? You are asked what is the size of the cube, right? So that is here, the question is like this, right? If there is a container like this and it is having some fluid, the cube was just below, it was just supporting, and just float means the cube was just floating like this, the cube was floating like this and was supporting 200 gram of weight above it. When this 200 gram was removed, the cube came above the surface like this with 2 centimeter above this much section is 2 centimeter above the water. You are asked what is the size of cube. Okay, so how would you do it? Again, it's a concept based question, right? So let's say the side of cube is L, right? The weight of the water which is displaced by the upper portion of the cube will be what? Weight is equal to mg, right? And mass is volume into density, right? So only 2 centimeters above, right? So only this much 2 centimeter, and there is L, right? So 2 into L into L, that is a volume. L cube, right? That is how you find the L volume. So above, weight of the water is displaced by the upper portion. The upper portion is this 2 into L, right? So mass I can write as 2 L cube volume into density, that is upper portion is displacing 1, right? That is the density of water into G, right? So how much it is? You are told 200 grams is what had been supported by this much portion. So that is equal to 200 gram. So from here you can find L as 10 centimeter. Right? If you don't understand, I'm going to take it again, guys. What happened is, initially this was inside the water, right? So and when 200 grams is removed, means this much portion has come out of the liquid. That is 2 centimeters L, and L centimeter has come out, right? So that means this 200 gram was actually supported by this much volume of the cube, right? Or this much weight of the cube. So 200 gram weight is equal to weight of this much portion of the cube, that is weight of 2 into L into L, right? So I can just write 2 into density of what? Why did I write density of water? So I can just write this much volume was actually inside the water, right? So the volume which was displaced by this much portion, right? If I want to find the weight of this much portion, right, I can just find how much is the weight of the water displaced by this much portion. That is, I have written as m into g, 2l cube, L1 into g, right? You will find L as 10 centimeter. Clear?